Okay, Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome back to another session. And in this one we are talking about collisions. So this is part two of booklet 19, unit 7.4, and we are talking about collisions. We will be focusing on inelastic collisions. Okay, so we'll learn about the difference in a minute. But we are not actually covering elastic collisions or perfectly elastic collisions in which kinetic energy is conserved. We will be talking about inelastic collisions. Okay, let's carry on. Bismillah. Okay, so what are collisions? So collisions are when two objects collide. So one of two things can happen. Basically, when two objects collide, either the objects bounce off each other, or they're going to stick together and continue moving in one direction or another. So basically, this is the situation that we have. So we have, let's say, for example, we have an object coming through this way, and let's call it object A, another object coming through this way, and we're going to call it object B. So one of two things is going to happen. Either after they collide, either object B and object A are going to bounce back, and that is what we call an elastic collision. An elastic collision is one where the objects bounce off each other. So I've got two plastic eggs over here. So if the two objects bounce off each other, that is called an elastic collision. What is an inelastic collision? An inelastic collision is one where the objects stick together and move along together. So when is that situation possible? When we have gooey substances, when we have a collision between two cars, so two cars that hit each other and then suddenly are mangled together and stick together, so that's quite possible as well. So those are the two situations when it comes to collisions. So when collisions happen, you can either have an inelastic collision in which the objects stick together, or you can have an elastic collision in which the objects bounce off each other. So that's the first thing I want you to understand. Okay, so and in the case where we have an elastic collision, the ideal elastic collision, in an ideal elastic collision, the kinetic energy would be completely conserved. Now, of course, in real life, that wouldn't necessarily be possible. The reason for that is here's an example that I'm going to demonstrate really quickly. So I've got two eggs over here. If we have the two eggs bouncing off each other, yeah? So this might look perfectly elastic to you, but if you listen carefully, do you hear the sound? That sound means that sound means that some of the kinetic energy has been converted to sound energy. And of course, some of it has been converted to heat as the two eggs hit each other, which means it's impossible to have a perfectly elastic collision under the situation or under the conditions here on Earth. We have air resistance, we have conversion of energy, right? So the energy is going to be converted. The kinetic energy, which means the movement energy, is going to be converted into heat, thermal energy, and sound energy, at least. So that's the reason why we can never have a perfectly elastic collision. However, of course, as is usually the case in physics, sometimes we talk about ideal scenarios, or sometimes we'll talk about a situation where we ignore air resistance and such. And that's what we mean in a perfectly elastic collision. However, in saying all of that, we are not covering elastic collisions. So we will be focusing on inelastic collisions in which the objects stick together and move along together as one mass. Okay, so a quick example of that would be a small car hitting a big car, and then the small car becomes embedded in the big car, and they move along as one object, as one mass, as one entity. Or a person tackling another person in football or rugby or American football, say, and then they stick together or they're holding on to each other. So those are the situations we'll be talking about, inshallah. All right, moving along. So we've already covered those actually. So inelastic collisions, as we said, is one where the objects stick together, they don't bounce off each other, and they move along as one entity. And elastic collisions, or completely elastic collisions in this case, is one where they bounce off each other and no energy is lost whatsoever. Okay, and in this case, the kinetic energy before and after would be the same. Uh, so that is, sorry, that is an elastic collision. So here we've got inelastic collisions and completely inelastic collisions. So those, both of those is when objects stick together as one lump. Hmm. So these are the collisions we'll be covering. In fact, sorry, I hope I didn't confuse anyone. We will be talking about inelastic collisions. We will not be talking about elastic collisions. Okay, let's move on. So the first thing you need to know and remember, hopefully, is that momentum is conserved. Momentum is conserved, which means it is saved. It will not be changed. The momentum before equals the momentum after. Momentum, if you remember from the previous session, is referred to as P for polarity or sudden strike. And so momentum is equal to mass multiplied by velocity. Okay, that is momentum, also referred to as P equals mv. Okay, so you need to know that. And so basically the momentum before the collision is going to equal the momentum, the total momentum after the collision. So that is the first thing I need you to understand. Okay, so momentum is equal to mass times velocity. And if we're talking about multiple objects, then it's going to be the momentum of the first object plus the momentum of the second object plus the momentum of the third object is equal to the momentum of the first object and the second object and the third object after the collision. Now, I'm just going to give you a quick example. So let's say, for example, here we have a multiple car pileup, okay? So here is a traffic light over here. We've got one car waiting at the traffic light. We've got another car that comes in behind the first car and hits it. Okay, so here we have a car that has just hit that first car and has become embedded in it. And then we have a truck that has come in here, in fact, and has also hit this car. And now we've got a multiple car pileup. Okay, we've got 1, 2, 3 different vehicles that have hit each other. Now we can consider this as one object after the collision, since they have stuck together and it's a perfectly inelastic collision. So that means now they will be stuck together. So in this situation, let's take some examples. Let's say the mass of the first car was 1,000 kilograms. So it's a quite small car. Let's say the mass of the second car is 2,000 kilograms, which is sort of an average car. And let's say the truck has a mass of about 4,000 kilograms. And let's talk about the speeds. So the first one was completely stopped, so that was stationary. So in this case, this is the mass, and the velocity of the first one was 0. Let's say the velocity of the second car was moving at perhaps 20 meters per second. Velocity equals 20. Now remember, we're talking about meters per second here. And let's say the truck was moving at about 18 meters per second. So the velocity of this car here, oh, let's make it easy. Let's, for calculation's sake, let's make it 10 meters per second. Now, the total momentum for each one is going to be calculated as such. So P total is going to equal P of the car, small car, so car 1, plus the momentum of car 2, plus momentum of the truck. And we've got all the numbers we need, so we can actually work it out, which is going to be 1,000 times 0, which is one big fat 0, plus the next one is going to be 2,000 times 20, which is going to be 40,000 kilograms dot meters per second squared. 40,000. And the third one, the momentum of the truck is also going to be 40,000, as it's 4,000 multiplied by 10, which is 40,000 once again. And so the total momentum is going to be 80,000. Now this is the momentum before the collision. I wonder, so then what is going to be the momentum after the collision? Turns out the momentum after the collision is going to be exactly the same as the momentum before. So this in fact is the momentum before, but it's also the momentum after. And since this is basically what we mean by the conservation of momentum, the conservation of momentum simply means that the momentum before equals the momentum after. And so if we know that fact, we can calculate all sorts of things, not least of which the velocity of moving objects and missing masses. Okay, just basically using that rule, the rule of conservation of momentum. Okay, so just to make sure that's clear, this is momentum before and momentum after, which equals P initial as well as P final. Okay, now I might turn around and say, okay, so what was the final speed then of all three vehicles combined together now that we formed some sort of train? All three vehicles are stuck together, what would be the final speed of all three vehicles? Now remember, momentum has a formula, and the formula is quite simple. P equals mass times V. Momentum equals mass times velocity. Do we have the total momentum? Yes, we do. It's 80,000. This is the total momentum. Do we have the total mass? We also have the total mass. The total mass is going to be 2 plus 4 plus 1, which is 7,000. Okay, so in fact, are they going to be moving together afterwards? Yes, they will be. Assuming that they stick together, they will be moving together afterwards. And they will be moving together at a speed of, let's see, this is a bit of an impossible situation I've created for myself, I've just realized. They will be moving at about 11, the whole mass of the whole thing will be moving at about 11 meters per second, just based on the situation that I have described. Although I've just realized that it's a little bit tricky the way I've described the situation, as the car's traveling a lot faster than the truck. And I'm hereby assuming that the car is going to collide with the first car before the truck joins in. But anyway, the situation is still true. The collision before, the momentum of the collision before the collision is equal to the momentum after the collision. Okay, let's move on. So I hope that makes sense. You add all the momentums to begin with, and it equals the momentum after. Oh, we're going backwards. Now just keep going forwards. So here's an example. We've got one on a touchdown attempt, 95 kilogram running back, runs towards the end zone at 3.75 meters per second. So what that means, the running back is just a term used for a certain player in football. So he's the running back, okay? And he runs towards a linebacker. So he's now this guy here is called a linebacker, and they're usually quite big. And he's 101 kilograms. So this guy here is 101 kilogram, 111 kilograms, sorry. Well, this guy here is 95 kilograms. And so they're running towards each other and they meet head on in a collision. And obviously, it says here they stick together. So you got to look for these words here. They stick together. What is the velocity immediately after the collision? Immediately after the collision. So how do we work out the velocity immediately after? Remember, P initial is equal to P final. Momentum before equals momentum after. Momentum before equals momentum after. So let's work out the momentum before. Also at this stage, I want to mention that momentum is a vector quantity. So obviously, since it's a vector quantity, it's going to be affected by the direction. So please make sure that you have the right direction when you're calculating momentum. So let's have a look here. So at this, if we take this as being positive, then we can take that as being negative, okay? Because we are talking about velocities here. So the velocity of the momentum of the linebacker, no, let's start with the running back. Um, running back is equal to the mass times the velocity. And assuming he is moving in the positive direction, it's going to be 95 multiplied by 3.75. And that is going to equal 95 multiplied by 3.75, which is about 350 or so. 75, and that is 356 per grams dot meters per second. Now let's work out the momentum of the linebacker. The momentum of the linebacker is equally going to be mass times velocity, which is going to be 111 multiplied by 4.10. So immediately I can tell his momentum is a lot bigger because he's got bigger mass and more velocity. So it's going to be close to 60 over times 4.10. So it's going to be, wow, that is quite a bit over 455 kilograms dot meters per second. Now the total momentum is going to be this plus this. Okay, but we have to be careful here because I forgot to put the sign over here. So I'm going to do that. So make sure you remember to put the sign. Um, and it doesn't matter which one you take as positive and negative as long as you keep the signs consistent at the end. So since I've taken this to be negative, all I have to do is P total equals 356 plus negative 455. I know there's no need for the parentheses, but it just makes it easier in my brain. It's just good practice for me. I like to use it. Negative 455, and that equals negative 99 kilograms dot meters per second. Are we done yet? No. We have one more step to go. So this is step one. This is step two. We have one more step to go. And the third and final step is that we need to remember they are moving as one mass now. So we need to divide, sorry, we need to divide momentum by mass to get the final velocity, because that's what it's asking us. It's asking us for their velocity immediately after the collision. Nearly there. So it's going to be velocity is equal to momentum over mass, which is equal to negative 99 over, really running out of space here, 111 plus 95, which is 216. 206, sorry. So that's going to be negative 99 divided by 206, and that's going to be, ooh, you're running out of space, negative 0.49 meters per second. Of course, what this means is that they will both be moving together to the left, is what they will be doing. And this makes sense because this guy is just so much bigger. So he's going to be holding the other guy and taking him, dragging him along towards the left at about half a meter per second, which makes sense. Okay, so that is the answer. Let's move on. Oh, we've got some follow-up questions here. The follow-up questions are as follows. We have, it says here, if the final speed of the two players is to be 0, should the running back be moving faster or slower, and explain? So the running back is the lighter of the two. So the running back is the guy in red, this guy here. And if the final speed is to be 0, remember now they're moving this way. Both of them together are moving that way. So if they want to be 0, then this guy has to be moving faster. because at the moment, this guy here is definitely has more momentum and he's dragging him more that way. So he has to be moving faster. And so in terms of should he be moving slower or faster? No, the running back should definitely be moving faster. Faster, so he can have bigger momentum, and of course, a bigger momentum would counter the linebacker's momentum to counter the linebacker. Because in order for them to be zero, the two momentums have to cancel each other out. They are vector quantities, so one of them has to be, if one is going at 456 and the other one is at 355, or sorry, 356 and 455, then it's just not going to balance. So they both have to be at 455, negative 455, positive 455, they will both be at zero. Of course, the next question is going to ask us to work it out, isn't it? Check your answer to problem number 42 by calculating the required speed for the running back. Well, that's very easy. Remember, we worked out the linebacker's momentum, this guy here, and he was negative 455. Negative 455. So this guy has to be the same. He has to be positive 455, same in magnitude. Positive 455 in order to balance that negative 455. So if we have negative 455 from this side, then we need to counter it with positive 455 from this side. But this guy is lighter. This guy has a mass of 95 kilograms. So in order for him to achieve this momentum with this mass, then his velocity has to be 455 divided by 95. So he has to be traveling quite a bit faster. He has to be traveling at 4.8 meters per second. And previously he's traveling at 3.75. So he has to be traveling faster in order to have a bigger momentum, which makes perfect sense. Okay, let's look to question 44. A block of wood is resting on top of the table and a bullet gets embedded inside it. What is the speed of the block and the wood? The block and the bullet after the collision. So we have the mass of the bullet and we have the mass of the block. And this is going to be 0.0105 and this is going to be 1.35. Oops, 1.35. So we have both masses, but we only have the velocity of the bullet. And if we have the velocity of the bullet, that's enough. Why is it enough? Because this is not moving. So the momentum before of the block is zero anyway. The momentum before of the bullet is going to be 0.0105, which is the mass multiplied by the speed or the velocity. So the total momentum of the system before is going to be the momentum of the bullet because the block is not moving. It's at zero anyway. So so taking that into account, excuse me while I fix my camera so you can see my face properly. So taking that into account, we can see that the total momentum before P initial is equal to 7.5075. And of course, we know that that is the same as the momentum after, the final momentum. Is it done? No, it's not. We need to know the speed of the bullet and the block together after the collision. It's going to be momentum equals mass times velocity. Do we have the mass of the block and the bullet? Yes, the mass of the block and the bullet equals 1.3605. So that is going to be 7.5075 divided by the total mass of the block and the bullet together. So it's going to be 1.35 plus 0.0105, which is 1.3605. And that is going to give me the velocity, which is going to equal 1.3605. And that is going to equal 5.5 meters per second. Makes sense? Okay, that's how you calculate that. Makes sense. Okay, question 45. I'm going to have to take question 42 away, and possibly question 43. Did that work? Almost. Yeah, might as well take question 43 as well. If you need to see those answers, you can always go back. That's the beauty of a video, is that you can always pause it and go back and look at the answers as you please. Let's look at question 45. A 1,200 kilogram car moving at 2.5 meters per second is struck directly from behind by a 2,600 truck moving at 6.2 meters per second. A small car is struck behind by a big truck. So the car is traveling at 2.5 meters per second, and the mass equals 1,200 kilograms, while the truck is moving at 6.2 meters per second and has a mass of 2,600 kilograms. So we can just work out, no, don't do that. So we can just work out the momentum of both, and that way we can work out their speed together after the collision. So remember, momentum is conserved, which means the momentum before equals the momentum after. So if I work out the momentum of the truck and then I work out the momentum of the car, and then I add both momentums, then that is the total momentum of the system before the collision. And then afterwards, it's going to be exactly the same. So it's 2,600 multiplied by 6.2. I hope you're doing this. It's a really good idea to try and do these. Pause the video and do it yourself, and then play the video and see if you get it right. Okay, so that's 16,120 kilograms dot meters per second. The other one's a lot easier to work out. It's only 3,000. But of course, the total momentum before P total is equal to 16,120 plus 3,000. Which equals 19,120. And once we have the momentum, that's the easy bit. That's the hard bit done. And then we just go back to this formula. So we go to, we need the velocity of both of them. So it's going to be 19,120 divided by the total mass, which is 3,800. The mass of the truck and the car, remember? And that will give me the velocity. So since we're looking at two significant figures, we can just stop there. That is the answer. I hope that wasn't too hot. Let's move on. A 950 kilogram red car with a speed of 16 meters per second approaches an intersection traveling in a positive x direction. This is the positive x direction. Um, a 1,300 kilogram blue van traveling 21 meters per second is heading for the same intersection in the positive y direction. Okay, I'm just going to write the masses here. And this is going to be 950. And then it says the car and the minivan collide and stick together. That is beautiful. They stick together. That means it's perfectly inelastic. Producing wreckage that moves at an angle of 61 degrees relative to the positive x-axis. Sixty-one degrees. Find the speed of the wreckage after the collision. Now, the difference here, of course, from the previous examples is we're not looking at the same axis. So before it was two things moving in the same axis. Now it's different. What do we do? This is where we use components. So there's three different ways you can do this. Yep, three different ways. Um, I'm going to show you all three. So the first way is to use the red car. So the momentum of the red car equals P red, which is equal to before before I work out the momentum. Remember, momentum is a vector quantity, and so you have the momentum of the red car, you have the momentum of the blue car. Let me be fancy. Momentum of the blue car. And then you have the momentum of what does red and blue do? Purple? That's both of them moving together. So I've got the angle. Since I've got the angle, I just need one of them to work out the momentum of both cars. So that's what I'm saying. Like if I use the red car, if I use the red car, if I know the momentum of the red car, which I do, 950 multiplied by 16, mass times velocity, and it equals 15,200. So this vector here is 15,200. And using that and the angle, remember SOHCAHTOA. Sorry, I don't know why I said that. But maybe now you'll remember it. Maybe I should say it again. SOHCAHTOA. Sometimes silly things work. Sometimes saying silly things like that makes you remember it. Anyway, so now I've worked out the momentum of the red car. I can work out the momentum of the purple, of both. How, Mister? That's the adjacent side. So cos theta. That's the worst theta I've ever done. Cos theta equals adjacent over hypotenuse. So the adjacent side over cos 61 equals the hypotenuse. So the hypotenuse, which is this guy, is equal to the adjacent side, which is 15,200, divided by cos 61. And so what that equals is 31,350. I'm just going to write the whole thing. So I'm just going to write it up here as well. 31,352. Now, that's not the answer, that's the momentum. And then I have to find P equals mv. So then I have to do that divided by the total mass, which is, what's the total mass of both those things together? It's going to be m is going to be 1,300 plus 950, which is 2,250. So what do I have to do? 31,352.5 divided by 30, 3250. And so the final speed is going to be that, the momentum divided by the mass, because here, okay, the velocity is equal to 31,350 divided by 3,250, which is equal to about 9.6 meters per second. That's one way of doing it. Another way of doing it is, instead of using the red car, I can use the blue car, and I wouldn't have the red car, so I just have 21 times 1,300. So that would give me blue, 27,300. And so this time it wouldn't be cos 61 or 15,200. It'll be sine theta equals opposite over hypotenuse, and that would be sine 27,300 over sine 61. And guess what? It would give me the same exact answer. About. I think they've rounded a few things over here when they were doing it. But yeah, it should give you the same answer. Of course, when you do it, it wouldn't give you the exact same answer, because it's quite obvious that whoever wrote the question made the mistake of rounding a few things up. But still, oh, I made a mistake, didn't I? Over here, it's 2,250. Nobody corrected me. Usually, the Senate corrects me, but I'm at home. Okay, so yeah, sorry about that. That's why it's important to check. But anyway, so once I do that, and then I do the same thing divided by the mass, 2,250, and then it gives me the same answer, which is 13.9 meters per second. But I reckon there's a third way. So we did it using the red car, we did it using the blue car, but there's a third way as well. Let's do it the third way. I know. The reason why there's a third way is because it's a right angled triangle. That's your clue. And since it's a right angled triangle, there's another rule I can use. Does anyone remember Pythagoras theorem? Okay, so let's go back to the beginning. I don't need the angle because it's a right angled triangle. I've got 950 over here, so I can work out 9 950 multiplied by 16, and then I can work out over here it's going to be 1300 multiplied by 21, 27,300, and 950 multiplied by 16, and that equals 15,200. And once I have both of these, I can work out this. It's simply a squared plus b squared equals c squared. So that 15,200 squared plus 27,300 squared, and then the square root of this big massive number, and that equals 31246. That is the momentum of both cars. And remember, it's PMV. And so the velocity is going to equal. Okay, hopefully that was seamless. Sorry, I had to pause the video and restart. So the velocity is going to be equal to the total momentum divided by, oops, no, let's go back. The total momentum divided by the mass, which once again, it's going to be the red car and the blue car together. So plus 950. And no surprises there. Same answer. So there you go. 3 different ways of doing it. Okay. Um, let's move on to the next one. Follow up. Suppose the initial speed of the red car in the guided example, 7.11, was greater than 16. Would the angle in which the vehicles move after the collision be greater than, less than, or equal to 61? If the red car was moving faster than 16, then obviously this is the red car. And if it's can I just use the red pen instead? So if it's moving faster than 16, you can tell that it's going to be pushing things a bit further away. So the angle would be less. And if it's moving really fast, maybe they would be moving that way, even that way. So it depends on how fast it's going, obviously. But if it's moving faster, it's going to have a bigger momentum and it's going to push the blue car even further that way. So instead of going like that, they might actually be going like that or like that. And so as you can see, the angle would decrease. So what would happen? What would happen? I don't know how to explain that one. I'll just say the angle decreases. The angle would be less. Angle would be less as the momentum would be bigger. As the momentum of red car would be bigger. Would be greater. God, my handwriting is terrible. Sorry, it's just writing on this glass. I promise you, like actual writing is not so bad. Explain. If I can write properly. Nope. Terrible. Suppose the speed, let's go to 47. Suppose the speed and the direction of the vehicles immediately after the collision in the guided example are known to be 12.5 meters per second. So this is both of them together now. 12.5 meters per second, and the angle is 42. Find the initial speed of each vehicle. Fine. So what we need to do here is work out we have the mass of both vehicles, which is 2,250. we have the speed, so we can work out the momentum. So we have the mass, which is 2250, and we have the speed, which is 12.5. So obviously we can work out the moment. 2250 multiplied by 12.5. So the momentum is going to equal 28,125. Knowing that, remember it's the triangle. So this is 28,125. I can work out, and then I have the angle. So I can work out this guy and this guy. And once I worked out both of these, I can work out, because remember this is 950, the mass. I can work out the velocity, and this is 1,300. I can work out the velocity. But first I have to work out the momentum. So let's go. 28,125, that's the hypotenuse, multiplied by sine 42, and that gives me, over here the momentum would be 18,819, divided by 1,300, and that gives me a speed of 14.5 meters per second. That would be the blue car traveling at 14.5 meters per second. And just using the same hypotenuse, I can use cos to work out the adjacent side, which is over here. So I can go cos 42 multiplied by 28,125, and that gives me 20,900 divided by 950, and this time the red car is traveling at 22, which makes sense. The red car would be moving much faster because the angle is less. And remember what we said, if the car was moving faster, if the red car was moving faster, then the angle would be less. Sorry. I know it's hard to read, but that says less. Okay, 48. An 82-kilogram football player is running in a positive y direction with a speed of 3.1 meters per second. Yeah, it's another one of those. Okay, so I'm going to need the space, so I'm going to take all of this away. Don't panic. If you need it, just literally go back. It's all there. It's all recorded. So, but I need the space. Okay. So we're just doing number 48. So here we have an 82-kilogram football player is running in the positive y direction. So that's last time I checked. That is there. And he is mass 82, speed 3.1 meters per second. A 96-kilogram player from the opposing team is running in the negative x direction with a speed of 2.4 when the tackle is made. So m equals 96 kilograms, and the speed, velocity, is 2.4. Assume the players remain together, so they stick together perfectly inelastic. What is the speed immediately after the tackle? So they are going to be moving somewhere this way. I'm going to try and make this perfect. Gosh, that is far from perfect. Okay, So yeah, they're gonna be moving that way. Okay, let's work it out. Let's work it out. Work it out. I could have done this better, couldn't I? Anyway, it's all the same. Um, what is the speed immediately after the tackle? So remember, I got to work out this momentum, and I got to work out this momentum, and then I got to work out this momentum, and I know the mass over here is going to be both of their masses together, 96 plus 82. Really good idea to do this yourself, as I said. So do it yourself and then check your answer with my answer. So the first momentum is going to be 82 times 3.1, 254.2. Always good practice to just get rid of the rounding and all of this at the end. And then the next one's going to be 96 times 2.4, and that's going to be 230.4. And and so you can choose how you can find this. This is whichever way. But I'm just going to use a squared plus b squared. So 254.2 squared, and then the square root, and then obviously that's going to be 343.1. There you go. Velocity is equal to momentum over mass, which is going to be the total mass this time because they are stuck together. How beautiful, they are stuck together. Okay, so that's going to be 1.93 meters per second. I didn't need the whole space. And if I wanted to work out the angle, that's pretty easy as well. That's just 254 over 230 shift tan or whatever. We can use any of the Sokatos. Oh, we are talking about this already. Fantastic. When a collision occurs, how are the initial and the final momentums of the system related? So hopefully you guys know how they're related. How are they related? They are related by, they are the same. So when a collision occurs, the final momentum and the initial momentum of the system are the same, as long as what? As long as there's no acting force, as long as there's no acting external force. So what does it mean as long as there's no acting external force? It means like the car hits another car and they stick together and then they move in a certain direction. As long as no other car comes and hits them, or as long as there's no rocket engines that go off, there's no external force of any kind, they just act on their own will, then the momentum is conserved. So 49, when collisions occur, blah, 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 momentum is conserved. Excuse me, I'm just going to look at my notes here. Um, as long as there are no external forces, then momentum is conserved. That is to say, P initial equals P final. Simple stuff, really. Phi 50. How is the initial kinetic energy related to the final kinetic energy in an elastic collision? Okay, so we're not doing energies, but if we were, it'd be the same. In a perfectly elastic collision, which is an unlikely scenario, then the kinetic energy is conserved. That means the speeds, the so not necessarily the speeds, but well, yes, the speeds, because kinetic energy is equal to half mv squared, and the mass is going to be the same, and so the velocities would be conserved because it's perfectly elastic. But we're not doing that. We're not doing that. We're not doing kinetic energy, so we're not going to do that one. 51. What happens to the kinetic energy that is lost in an inelastic collision? With inelastic collision, again, we're not doing kinetic energy, but it would go into deformation, it would go into heat, it would go into sound, it would go into other forms of energy. So, once again, we're not doing that. But yeah, momentum is conserved. Kinetic energy is not conserved in an inelastic collision. 52. Identify what do we call a collision in which the colliding objects stick together? An elastic? I had to check my notes just to make sure. Am I losing it? Got my notes right here. Um, 53, the big idea. What condition is required for momentum to be conserved in a collision? Okay, so really the big one is no external forces. That is to say, there's nothing acting on the two objects when they collide together. They collide together, there's no air resistance, there's no external forces, there's no one else pushing. Imagine like two toy cars hitting each other and then immediately stick together, that is an inelastic collision, or they bounce off each other, that is an elastic collision. Either way, momentum is conserved. Both elastic and inelastic, momentum is conserved. The only thing is kinetic energy is not conserved in in an elastic collision, in an inelastic collision, sorry. But don't worry about that. But momentum is always conserved. However, as long as even with those toy cars, as long as I don't give it a wee push afterwards. Because then, in the moment you give it a wee push, it's like, of course, it's not conserved anymore. It's a bit like that example with the bowling ball that's hanging in a pendulum, right? If you let go of it, it's going to go and then it's going to come back and it's not going to hit you in the face. Why is that? Well, because in this case, in this instant, the energy is supposed to be conserved and the momentum too. But if somebody gives it a wee push, okay, or as it swings back, somebody gives it a wee push, then it's no longer conserved and it can actually hit you in the face. So, as long as no external forces are acting on it, then momentum will be conserved. That's the main one. No external forces, closed system. And 54, assess two cars collide as an intersection. If the cars do not stick together, can you conclude that the collision was elastic? Um, hmm, yes, two cars collide at an intersection. If the cars don't stick together, can you conclude that the collision was elastic? No, it doesn't have to be perfectly elastic. So while elastic collisions result in the two objects bouncing off each other, um, yeah, so I think it could either be perfectly elastic or could be partially inelastic. And this is where kinetic energy would play a role. And if the kinetic energy is completely conserved, that is to say, before and after it's the same, then the collision is perfectly elastic. However, if the kinetic energy is not conserved, that means part of the energy has gone into sound and heat. And if that happens, then it's not completely elastic. Once again, that's got to do with energy. So don't worry about that one. So just quickly, briefly, let me explain that one the way I just use the eggs. So I want to know if this is perfectly elastic. I'll calculate the energy before and after. Okay? And if I find that the energy before is equal to the energy after, which by the way would be impossible if they were making sound as they are now, assuming they don't make sound, then there is a chance that this is a perfectly elastic collision, but only if the energy before equals the energy after. Not that you need to worry about that. Some calculations. Thank God. Um, Brittany stands at rest on a skateboard. Here's Brittany on a skateboard. And the combined mass of Brittany and the skateboard is 61 kilos. 61 kg. Dave tosses a 3.7 kilogram pumpkin to Brittany and she catches it and the skateboard begins to roll backwards with a speed of 0.16. So, oopsie, sorry. So, here's Brittany holding the big pumpkin and she's very happy with herself. Now, she starts rolling backwards with a speed of 0.16 meters per second. What was the speed of the pumpkin? Okay, so in this case, we don't know the momentum before, but we do know the momentum after. How do we know the momentum after? Well, that's going to equal um, her mass with the skateboard as well as the mass of the pumpkin. So it's going to be 61 kg plus the mass of the pumpkin, which is 3.7 kg, and that equals 64.7 kilograms. And so we know momentum equals mass times velocity. So it's going to be 64.7 multiplied by 0.16, and that equals 10.352. That is the total momentum after, which equals the total momentum before. So all I have to do is divide by the pumpkin. Why not divide by Brittany? Because Brittany wasn't moving. Look, it says here she was standing at rest. So only the pumpkin was moving initially. So the pumpkin was moving and she wasn't. So all I have to do is divide that momentum by the mass of the pumpkin, which is 3.7, and the pumpkin was moving at 2.8 meters per second. My apologies for not writing the full workout, but I think I would like you to struggle a little bit and try and figure it out. Hopefully it'll make sense to you. It'll make you understand it better. Well, I think that's it. Okay, thank you very much. I hope you have enjoyed that. Take care. I'll see you in the next one.